So let's continue this iron carbon equilibrium diagram. So in this, we have three invariant reactions. Here, eutectic reaction, where liquid is directly converted to two solid. So first one is eutectic reaction, where liquid phase the iron carbon mixture on cooling converted to two solids. What are the two solids? Gamma, that is austenite, plus Fe3C cementate. Okay, so this is the first invariant reaction, eutectic reaction. And second invariant reaction is eutectode reaction. Eutectode reaction. And in this eutectode reaction, here this is the point of eutectode point. Corresponding line is called eutectode line. Here, one solid, that is austenite on cooling converted to two austenite on cooling converted to two other solids. What are the two other solids? Alpha ferrate plus cementate. So this is the second invariant reaction. And third invariant reaction is peritectic reaction. Peritectic reaction. So this is the peritectic point. This one is the peritectic point. What happened here? The L plus delta, which is in this region. Okay, when it is crossed the peritectic point, it is converted to a single phase solid, that is gamma. Okay, so liquid plus one solid converted to another solid. Okay, so liquid plus the delta ferrate on cooling is converted to another solid, that is austenite. Okay, so this is the three invariant reaction we can see in this iron carbon equilibrium diagram. Okay, so corresponding line is eutectic line, sorry, eutectode line, and peritectic line. And here also we can see different phases also. What are the different single phases? Single phases we can see in this iron carbon equilibrium diagram. Single phases. First one is liquid phase. A mixture of iron and carbon, that is a liquid phase. So that is the first phase, single phase. Another single phase we can see in this region. This is delta ferrate. Delta ferrate, which has BCC crystal structure. And another phase is gamma austenite. Austenite, gamma. And another phase we can see is alpha. So alpha ferrite. These are the four single phases present in the iron carbon equilibrium diagram. Okay, and one more compound also present, that is Fe3C. Fe3C is a compound called cementate, and which is this line belongs to that compound Fe3C. Okay, this line belongs to that compound Fe3C, cementate. Okay, and what are the different two-phase regions? Two-phase region present in iron carbon equilibrium diagram. The first one is this one, alpha plus Fe3C. We can see two phases here. Okay, alpha plus Fe3C. Another one is gamma plus Fe3C. Gamma plus Fe3C. Another one, liquid plus Fe3C. Okay, then another one is delta plus gamma. Delta plus gamma. Next one is L plus delta. L plus delta. L plus delta. And this another one is gamma plus liquid. Gamma plus liquid. So these are the different 1, 2, 3, 4, 5, 6. 6 two-phase regions is present in the iron carbon equilibrium diagram. Okay. Any doubt in this? Up to 2.1%, 14%, this region belongs to steel. That means the carbon composition for a iron up to 2.14% of carbon belongs to steel region. And after this, from 2.14 to 6.67, that is the cast iron region. Okay, so when we add above 2.14% of carbon into iron, the resulting material is cast iron. Okay, cast iron region. And we can see in this cast iron region, this is the region of lowest melting point region. Okay, cast iron region is the region of lowest melting point. So that is one of the advantage of casting process. Okay, in the casting process using cast iron, we can at a very low temperature we can convert liquid into solid. Okay, this is an advantage of casting process. Any other doubt? So this 912 and 1394 and 1394, 1538. These are the polymorphic transformation temperature of the iron, pure iron. This line belongs to pure iron, and this line belongs to the cemented compound. Okay, and we can see the iron carbon, different composition of iron and carbon, and the corresponding phases develop in this region, in between these two lines. Okay. So next, these are the, and this process is reversible. All these processes are reversible in nature. This process, we can reverse this process by heating process. Okay, that is actually what we do in heat treatment process. We heat the material from this state or this phase to any higher state with a higher temperature by heating process. Then we allow to cool in a fast rate or slow rate. Thereby we get different types of crystal structure. Okay, that is the heat treatment process. So this, all these processes are reversible process. By heating, we can convert this two solid into liquid also. Okay. And this austenite, actually, this phase diagram is constructed by a scientist called Robert Austen. And for honoring this Robert Austen, this phase, we give the name of this phase as austenite, the last name of Robert Austenite. Okay. And so these are the invariant reactions. And in this phase diagram, iron carbon equilibrium diagram, the most important region is this region, this region, the eutectoid region. Okay, and the reason is that almost all the heat treatment process we carried out in this region. Actually, by doing different heat treatment process, we can change the microstructure of the steel. Okay, and so all this heat treatment process which we are going to do in the steel is in this region. First, we convert it into recrystallization temperature or above recrystallization temperature. It may reach into austenite state or any gamma plus Fe3 state. Then we cool this into a required microstructure. So all this heat treatment process carried out in this region. So this region is very important for studying the or for varying the microstructure of the steel. Okay, so we are specifically analyze this region of the iron carbon equilibrium diagram. So this is the region. This is the this part of the iron carbon equilibrium diagram. Okay, and here the concentration is somewhat different. 0.76, it is rounded to 0.8. Okay, and this is also 912. Here it is 910. But you follow this temperature and composition. Okay, so here we can see alpha. This is alpha. This is alpha plus gamma. Alpha plus gamma. Alpha plus gamma. And this region is austenite, and this area is gamma plus Fe3C. Okay, we can see gamma plus Fe3C, and here this region is gamma plus Fe3C. Sorry, alpha plus Fe3C. Okay, and the different single phases present in this iron carbon equilibrium diagrams are the delta ferrate. Okay, and here we can see what is the maximum concentration of carbon in delta ferrate. Maximum concentration of carbon in delta ferrate. That is, we can see here, that is 0.1% of carbon. This point. Okay, this point. 0.1% of carbon. Okay, but here, what is the maximum percentage of carbon can accommodate by alpha ferrate? That is equal to 0.02. 0.02%. Okay, so there is a difference here. Both the alpha ferrate as well as delta ferrate has BCC crystal structure. Both has BCC crystal structure. Okay, so the crystal structure is same, but delta ferrate can accommodate more carbon in its interstitial sites than that of alpha ferrate. What is the reason for that? Both are same crystal structure, but delta ferrate can accommodate 0.1% of carbon. When compared to this alpha ferrate, they can only accommodate up to 0.02% of carbon. What is the reason for that?
High temperature.
Yes, at the high temperature, the interstitial walls, the carbon atom can easily enter into the interstitial wall space, because at the high temperature, the iron particles vibrate at a very high amplitude. So carbon particles can easily enter into the interstitial sites of the crystal structure of iron. So that is why here in the delta ferrate, we can accommodate more carbon than that of the alpha ferrate. Okay, and here we can see in case of gamma arsenate, we can the carbon can 2.14% of the carbon. Okay, very high percentage of carbon can accommodate by gamma arsenate. The reason is that it has FCC crystal structure. Okay, so FCC crystal structure, the whole space is higher in case of FCC crystal structure than that of the BCC crystal structure. That is why the arsenate or gamma iron can accommodate more amount of carbon. Okay, so that is about the three liquid, delta, gamma and alpha are the three single phase regions present, and of course this cementate also, that is a compound, is called intermetallic compound of iron and carbon, and it has orthorhombic crystal structure. We already studied this crystal structure, orthorhombic, right? There are 7 types of crystal structure, crystal system. In that orthorhombic crystal system for Fe3C or cementate, which has orthorhombic crystal system. Okay, it is an intermetallic compound. We will study in detail about intermetallic compound in the last module. So these are the different single phases region present in the iron carbon equilibrium diagram. Okay, and this is the picture showing arsenate and ferrate. This is the alpha ferrate. This is alpha ferrate, and this one is arsenate. Okay. So these are the phases present. Alpha ferrate, interstitial solution of carbon in BCC. Maximum solubility is 0.025%. Okay. It is existing between 273 degrees Celsius to 910 degrees Celsius. It's not at room temperature. Okay. And this line only up to this line. When we extend this line, we can this line coincide with this y-axis at 273 degrees Celsius. So we cannot see alpha ferrate in room temperature. Okay, so this is 273 to 910. So 273 to 912 degrees Celsius. It is 912. So you have to study this temperature 912. There will be variation depending upon the purity of the iron. The temperature may vary. So in different textbook, we can see different temperature values, but you follow this temperature, that is 912 degrees Celsius. So we can see the alpha ferrate region from 227 degrees Celsius to 912 degrees Celsius. Okay, and the second one is gamma ferrate. Gamma ferrate is a carbon interstitially occupied in the FCC iron, and where the 2.14% of carbon can accommodate by arsenate phase. Okay, and what is the temperature range for austenite? It is 912 to 1394. Okay, that is for pure iron. But here we can see it in this austenite is the maximum variation is between 727 to this 1493. This is the variation of austenite. Okay, but in very low concentration, we can say it is in between 912 to 1394. And last one is delta ferrite. It is again a BCC crystal structure. It is in the high temperature region and maximum solubility only 0.01. Okay, and the cementate is an intermetallic compound with a composition of carbon 6.61%. Okay, and also the graphite, the pure form of carbon, that is called graphite. Yeah, graphite also may somewhere in this iron carbon equilibrium we can see graphite also. Okay, the free carbon also can be seen in this without any formation of phases or compounds. The free carbon also in the form of graphite can see in the iron carbon equilibrium, but this concentration is very low, so we neglect the graphite presence in the iron carbon equilibrium diagram.
സാറേ അത് വരുവാണെങ്കിലും അങ്ങനെ മൂലയിലല്ലേ വരത്തുള്ളൂ?
Yeah, the graphite. Yeah, yes, yes.
Graphite.
Go this side. Yes, yes, yes. Okay, so these are the again the same content. So these are the phases present. And again, so next coming to this area, this is the steel area. So in this steel area, I can divide this steel area into three. Okay, and the first one is eutectode steel. So this eutectode steel is corresponding to this composition. Corresponding to this composition, that is 0.76% of carbon is called eutectode steel, where the composition of carbon is 0.76%. Okay, so that is eutectode steel. And to the left of this, similar to the copper nickel diagram, to the left of the eutectode line or composition, this region is called hypoeutectode steel. That is the percentage less than 0.76%. Okay, the percentage of carbon less than or 0 to 0.76% is called hypoeutectode steel region. And the region between these two, that is from 0.76% to 2.14%. This region is called hypereutectode steel. Okay, so the carbon percentage is greater than 0.76 and up to we already discussed this steel is up to 0.14 only. So this region from eutectode steel to this 2.14% of carbon, this region is called hypereutectode steel. Okay, so we are going to study this region, this eutectode region, your hypoeutectode region and hypereutectode region during the heat treatment process. So you have to remember these terms, eutectode point, and this is the corresponding eutectode composition 0.76 and less than 0.76 is called hypereutectode steel and greater than 0.76 is called hypereutectode steel. Okay, we already discussed the critical temperature of P3's diagram, eutectode temperature, the horizontal line temperature corresponding to horizontal lines, that is this temperatures. Okay, we already discussed that. So peritectic reaction, carbon, we already discussed this, and here how this percentage, we got this percentage. For example, peritectic reaction that is happening in the 1493 degrees Celsius, and in this 1493 degrees Celsius, this percentage we got from here we can see liquid, that is 0.53 percentage of carbon. So if you take a peritectic reaction, for example, this is my peritectic reaction, and here this one is the peritectic reaction. So above this line, we can see from the diagram, above this line, see this is the horizontal line. Above this line, the composition is liquid plus delta. So this is liquid plus delta, and this temperature is this 1493 degrees Celsius, that is the peritectic line temperature. And when this is the peritectic point, when it is crossed, the liquid plus delta cross the peritectic point, here what is the constants? The delta plus gamma. Delta plus, sorry, it is gamma. Okay, when it is crossing, it is gamma. So here one solid and a liquid changes to another solid gamma. Okay, and here we can see the 3 points in this line. These are the 3 points in this line. Here this is 0.5 percentage, and here it is 0.1 percentage, and here it is 0.2 percentage. These are the 3 points. We can see 3 points here. 3 points here. This is the first point, second point, third point. Okay, and 3 points are represented here. Corresponding composition of carbon is 0.1 percentage, 0.2, and 0.5. Okay, and how we got this equation? So from this diagram we got this equation. Here at the peritectic reaction, what is the liquid concentration? Concentration or composition of carbon in the liquid, that is equal to this value, 0.5. Okay, this is a rounded value, 0.5. Actual value is 0.53. And delta, that is equal to 0.09 or 0.1 percentage. This is 0.1 percentage. Okay, that result into, when it is crossed the peritectic point, we got gamma. Gamma, what is the concentration of gamma? Corresponding to this point, draw a line vertically. Sorry. Draw a line vertically from this point to here. Okay, draw a line from the peritectic point to know the carbon percentage. So we got this value 0.17 percentage of carbon. Okay, so this region is not there is no engineering importance for this region, because this is at a very high temperature. This peritectic region is at very high temperature. Okay, so there is no engineering importance for this this region or peritectic reaction. Okay, all materials, when it is cooled, it's reached below this our room temperature. Okay, or all heat treatments is actually we done in this region. We are not going up to this region. So this is not an engineering important region. So we are not considering this region for further study. Okay. And this eutectic reaction, here in this eutectic reaction, what happened? The liquid with the 4.53 percentage of carbon. Okay, so this is liquid with the 4.53 percentage of carbon is converted into gamma with the 2.14. Take the end of the, to know the percentage of 2 components. For gamma, take this end, 2.14 percentage. That is 2.14 percentage. And Fe3C, which is at Fe3C, which is at 6.67 percentage. Okay, so Fe3C 6.61 percentage. Okay, and this mixture, and we have another name for this mixture, gamma plus Fe3C, and this mixture called lidoberate. Okay, this mixture is called, so another name for this mixture is called, another name is lidoberate. Okay, lidoberate. This mixture name is called lidoberate. Okay, and again here also we can divide into 2 regions, the composition to the right and the left, the hyper-eutectic and the hypo-eutectic stream or gas stream respectively. Okay, so here this is this line is the eutectic composition. Eutectic composition. To the left of this eutectic composition, that is hypo-eutectic composition. To the right of this composition, that is hyper-eutectic composition. Okay, so that is this reaction. Here also we can divide into hyper and hypo, but this area also not important for any engineering application. Okay, our importance is in this region, that is eutectode region. So in the eutectode region, the gamma is converted to 2 solids, the alpha and Fe3C. How we got this percentage? Gamma, which is at 0.76 percentage. This is rounded value 0.8. Actually, it is 0.76 percentage. When it is cooled, it is converted to gamma alpha plus Fe3C. How we got the percentage of alpha? Take 3 points of this horizontal line, and this endpoint composition is the percentage of alpha. That is equal to 0.02 or 0.025. Okay, so this one is the percentage of alpha. And for Fe3C, again, this third point, this is here. Okay, and this percentage is 6.61 percentage. Okay, so again, already I explained this can be divided into two, hypo-eutectoid and hyper-eutectoid region. Okay, so that is the eutectic reaction. You have to study these three reactions. It's very important. Next, we are going to discuss the microstructure changes in the iron carbon equilibrium diagram. When we cool from one phase to another phase, what happened to the microstructure of the different constituents of the iron carbon equilibrium diagram? So we will study about that. In that, I am taking different reaction points. Okay, so here the microstructure of the eutectoid composition. What is the eutectoid composition? This one. So when I cool from this point, this is my point A. So here in this diagram we can see the point A. Okay, when I cool in this direction through the eutectoid point, what happened to the microstructure of the constituents or steel? Okay, so that is I am going to explain here. So here in this, so here this is the region of this iron carbon equilibrium diagram. I am explaining this region. I am explaining this region. Okay, this region. So this is that the separate region. Here, this is the region. This is the eutectoid point. This point, 0.76%. Okay. So in this region, what happened to the microstructure of the constituents? So here in this region, we can see this at this point A, this is an austenite phase. Okay, austenite phase. So this is my point A. This is my point A. This is austenite phase. That is a single phase. Only single solid can see in this phase. That is austenite, gamma. Okay, and this is also a solid phase. Okay, so during the when liquid is converted to this gamma, this is a single phase solid solution. Okay, so we can see a polycrystalline material similar to this. This is a polycrystalline material. We can see different grains in that. This is not a single crystal because during the solidification process, what happened during the solidification process? Initially, all are liquid. All the mixture, the iron and carbon mixture is in the liquid form. This is the liquid form. Okay, when I cool, what happened? When I cool this, some nucleus of the gamma austenite solids will be formed. Okay, some nucleus is formed randomly on the liquid regions, and this nucleus starts to grow in different orientation direction by dendrite growth. This nucleus starts to grow, and finally different grains we got. We got different grains with the different crystallographic orientation. We got different grains. So such a microstructure is shown here. A polycrystalline material of single phase gamma is developed at point A. Okay. So when such a gamma microstructure, polycrystalline material, when it is crossed this eutectoid point, this is the eutectoid point. What happened to the microstructure? Here we can see already from the iron carbon equilibrium diagram we studied when here it is gamma, but here it is alpha plus ferrite. Okay, alpha plus ferrite. That means we have to gamma should convert into alpha plus ferrite. Okay. So already we discussed the microstructure of gamma. This is a single phase microstructure of gamma. So this microstructure should convert into alpha plus ferrite. Okay, when it is crossed the eutectoid point. Okay, so what happened to this? When it is crossed the eutectode point, we got this type of microstructure. This is the microstructure after crossing the eutectode point. Here, the two separate phases are formed. This is a multi-phase region. Alpha is the first solid, Fe3 is another solid. Okay, there are two solids to be there, but here in this case, here it's a single solid solution. We cannot see another solid here. Only single solid solution is formed here at the gamma phase or austenite phase. But here, when it is cross the eutectode point, here we can see two mixtures of solids. One is alpha, second one is cementate. Okay, and the arrangement of the constituents is like this, the microstructure. And here we can see the red colored. The red colored one is the cementate. Okay, so this is the cementate. It is like a plate structure or laminar structure, lamellar structure. Okay, so the red colored plate-like or layered structure is called, and that is ferrite, Fe3C. Okay, and the remaining, the gray color, this gray color structure is the alpha. So there will be a boundary between alpha phase and Fe3 phase. Okay, there is a separation region between alpha and Fe3C. Okay, Fe3C, this is a lamellar or layered type of structure, cementate and alpha. So this is the microstructure after crossing the eutectode point. So this is the microstructure of the alpha plus Fe3C. Okay, any doubt? Okay.
Sir, point cross
The point. The point is just cross actually what happened in this that here in the gamma region, in the gamma region we have an interstitial solid solution of iron, carbon in iron. So this is the gamma region. It's a perfect solid solution. The carbon occupy in the interstitial positions of the iron. Okay, this is the gamma single phase solid solution. When it crossed this eutectode point, what happened is that this some of the carbon from this interstitial position come out. Okay, when it is crossed the eutectode point, some of these carbon atoms in the interstitial position come out and it react with the iron. It react with iron and form Fe3C. Okay, this carbon from the interstitial point position come out and it react with the iron and form Fe3C. And this Fe3C is this red colored or the layered structure. And the remaining material without or minimum value of, that means here we can see in case of austenite, how much is the percentage of carbon from the iron carbon equilibrium diagram? That is 2.14. The percentage of carbon is 2.14. Okay, this is 2.14, the percentage of carbon. But here when it is crossed this, what is the percentage of alpha, carbon in alpha? That is only 0.02 percentage. So remaining carbon particles, that is the difference between 0.02 percentage of carbon and 2.14 percentage of carbon. There is a difference. And this quantity of carbon come out from the interstitial position and react with this iron and form Fe3C. So after forming Fe3C, this will be the crystal structure. The number of atoms, carbon atoms present in the iron interstitial position will be very low, that is 0.02 percentage. So this is alpha. So alpha plus Fe3C is formed. Okay, so 2.14 percentage of carbon which is occupied in the interstitial positions of the iron in the gamma state. Okay, when cross the eutectode point, what happened? This interstitial carbon atom come out and react with the iron, form Fe3C compound. Okay, and remaining carbon atoms present in the iron is only 0.02 percentage. That is the alpha value. Okay, so alpha plus Fe3C is formed. And this alpha is like a matrix in this microstructure, and layered structure of Fe3C can be in the seen in the microstructure. Okay, clear?
Okay, sir. Clear. Thank you.
So this is actually what happened. This is the actual picture of this microstructure of alpha plus Fe3C. This one, and here we can see a thin layers of with the light phases are present with the alpha ferrite. These light phases, okay, the white color light phases are alpha ferrite, and the Fe3C is actually thin layers of most of which appears as dark. Okay, so this dark colored layered structure is Fe3C. So this is the actual picture of the eutectoid steel. Okay, so this is the mechanism of this diffusion process. I already explained that mechanism. See, here we can see the alpha, the interstitial carbon come out and form Fe3C. Okay, and the remaining part is the alpha. Okay, so from 2.14% of carbon, out of this almost 2.13% is come out and form a compound with iron. The remaining part is called alpha. So that diffusion process is actually shown here. Here we can see in this region it is alpha. Okay, alpha. In this alpha, sorry, this is region is gamma. In this gamma, the carbon concentration is very high. Okay, and this high carbon, what happened? It is moved towards this blue color Fe3C, or diffuse towards the blue color Fe3C. The Fe3C required more amount of carbon. So all the carbon from the austenite phase diffuse into Fe3C, and finally we got a ferrite structure, alpha ferrite structure. Yes, so the diffusion direction is like this. From the alpha, all the carbon move towards the Fe3C, cementate. Okay, so this is actually a diffusion process happen when it is crossed the eutectoid point. Okay. So next microstructure is this one, the hypoeutectoid steel. Hypoeutectoid steel. Already I explained what is hypoeutectoid steel in this iron carbon diagram. See this in the iron carbon diagram, this region. So the last microstructure is along this line, that is eutectoid steel, and next one is this region, that is hypoeutectoid steel. So when I draw a line through this, like this, when I draw a line like this is the corresponding variation in the microstructure along the line. Okay, so next I am going to explain this microstructure variation, and when it vary along this line, what happened? So when it vary, here we can see this is the line passing through the hypoeutectoid steel. Initially at point A, this is the point A. Okay, at point A we know that similar to the previous case, the gamma austenite single phase region is present at point A. Okay, and when it is crossed this line, cross this curve, when it is crossed this curve, we got another point D. Sorry, this is point D. Okay, when we cross the point. So what happens is that there, when it is crossed, here it is gamma. Here in this region it is gamma plus alpha. Okay, that means some of the gamma present in at A changes to alpha. Okay, some of the gamma present at A changes to alpha. Okay, so how this change happen? Here when it is crossing, here we can see these alpha particles segregate in the grain boundary regions of the gamma. Okay, so here we can see in this picture, we can see these are the grain boundaries. The blue colored ones are the grain boundaries. and alpha particles with a low concentration of carbon, okay, segregate in the grain boundary regions of gamma. Okay, when it is crossed this curve, M0 curve. Okay, so a two-phase region is developed. So some gamma phase are there, some alpha phases with the very small regions of gamma along the grain boundary is formed. Sorry, small region of alpha along the grain boundary is formed. Okay, so the major proportion is gamma austenite and alpha ferrite is along the grain boundary. Okay, again when we move down or during cooling process, we reach point E. At point E, the concentration of this alpha is increased. Okay, the concentration of alpha, that means much amount of this gamma converted into alpha. Okay, so there are most of the gamma particles convert into alpha, and the gamma particles is actually formed along the grain boundary. Sorry, alpha particles is formed along the grain boundary of the gamma. Okay, so this size of this alpha phase increased, and when it is crossed this eutectode line, when it is crossed the eutectode line, it's very important. This alpha phase, which is formed at this point E, it will be maintained like that. Here we can see the alpha phase which is formed at point E, this orange color one, and which is actually maintained there at point F also. There is no change in the alpha phase, but we can see there is a gamma quantity, remaining gamma quantity. This gamma convert into alpha plus ferrite, similar to the previous case. Here we can see, here we have some gamma phase. This gamma when cross this point or this line. Okay, if it is cross this point, here it is across this point, but similar microstructure will be developed when this gamma cross this line also. Okay, so up to this point E, just before this line, just above this line, up to point E, this is the microstructure. A alpha phase is along the grain boundary, and gamma phases, we can see some of gamma phases also. And when we cross this line, this eutectode line from E to F, what happened? There is no change in the microstructure of the alpha phase. We can see the alpha phase similar to the point E. But this gamma phase, what happened? Similar to this eutectode reaction, all the gamma phase converted to alpha plus ferrite, similar to this lamellar structure. Okay, so here we can see remaining gamma converted to this lamellar structure, alpha plus ferrite. So here we have two types of ferrite. What are they? The ferrite which is formed here, and that ferrite is called pro-eutectode ferrite. The ferrite which is formed above this eutectode line, this orange colored one, that is pro-eutectode ferrite. Okay, another ferrite also formed when this remaining gamma cross this line, horizontal line. That is this gamma eutectode. Sorry, when this gamma crosses the eutectode line, some alpha will be formed. That alpha is called eutectode alpha. So two ferrite is formed, two alpha is formed, pro-eutectode alpha as well as eutectode alpha, and Fe3 is also formed. So this is the microstructure after crossing this eutectode line. Understand? മനസ്സിലായിരുന്നോ?
പേളൈറ്റിന്റെ കാര്യം പറഞ്ഞില്ല.
Sir, the main difference in the eutectode and pro-eutectode.
അത് മനസ്സിലായില്ല അത് യൂട്ടക്ടോഡ് പ്രോ യൂട്ടക്ടോഡ്. ഇവിടെ ഈ പിക്ചറിൽ നോക്കൂ, ഞാൻ വരച്ചാണില്ല. So when the this point B, this point is B at here. This is the point B, just above this eutectode line. This is point B, just above eutectode line. Okay, at point B, this is the microstructure. At the point B, at the point D, this is point D. Okay, at point D, what happened? In the grain boundaries, alpha form G. Grain boundaries alpha ferrite form G. That is at point D. When it's reached the point B, just above this eutectode line. Okay, so this will be the microstructure. I will show it another color. This is the microstructure. Along the grain boundary, the entire grain boundary, this alpha starts to grow from D to B, and this is the alpha value. Alpha, the remaining materials are gamma. This red color is alpha, and remaining material is gamma. Okay, so this is the state at point B. Okay, when it is crossed the point, this line, this eutectode line. Okay, when it is crossed the eutectode line, nothing will happen for this alpha. And alpha ku change indavilla. Adinu parayunnana ee alpha ku parayunnana without any change. When it is crossed the eutectode line, there is no change in this three red color alpha. So this alpha is called pro-eutectode alpha. This is called pro-eutectode alpha. That means pro-eutectode means eutectode ettunnadinu mumbulla alpha. That is pro-eutectode alpha. There is no change in this alpha. This red colored alpha, when it is crossed this eutectode line, okay, it's remain as same. But what happened to microstructure when it is crossed the eutectode line? That is at point C. Point C. Here remaining part is gamma. These are gamma. Other than this red color, all these things are gamma. Single phase oscillate. Okay. And when this, there is nothing will happen for this pro-eutectode alpha when it crosses the eutectode line. But this gamma, when it is crossed the eutectode line, similar to the previous case, this conversion will happen. When gamma cross the eutectode point, what happened? Such type of alpha plus ferrite lamella structure is formed. Okay. Similar microstructure change will happen when the remaining alpha, when this remaining alpha cross the eutectode line. Eutectode line and the eutectode point is actually same in terms of microstructure change. Okay, so similar microstructure change is happen when the remaining gamma particles, other than this pro-eutectode alpha, we have some gamma particles. This gamma particles, when cross this eutectode line, what happened? This gamma convert into this type of shape, some alpha as well as this Fe3C. Okay, so that is I am going to draw. So this is the at the point C. At point C, at point C, this is the pro-eutectode alpha. There is no change in the pro-eutectode alpha, similar to the previous case. Here we can see there is no change in these two pro-eutectode alpha. But this gamma converted like a previous case, like this. This remaining gamma convert like this. Okay, how? Like so these are the three pro-eutectode alpha. I will take another. So this will be the microstructure. So remaining gamma particles converted to alpha plus ferrite. Okay. So this red colored is, green colored is the gamma which is formed. The gamma which is formed by the eutectode conversion. The green colored. Okay, and the white regions are, the remaining white regions are Fe3C. So these white regions are Fe3C. This green colored is alpha, similar to this case, which is formed, this green colored alpha and this Fe3C is formed from this gamma when it is crossed this eutectode line. Okay, and this red colored pro-eutectode alpha is already formed at this point B. Okay. So that is the microstructure change. So this alpha plus ferrite, the green color and white color, and this is collectively called palite. This is collectively called palite. Okay, its structure, when we see this microstructure through a microscope, it is like a palite structure, the mother of pearl structure. So that is why this name palite structure we can see in this alpha plus ferrite. Okay, so at the point F of the hypoeutectode steel, we have three micro constituents. It's not phases, micro constituents. That is, one is pro-eutectode alpha, then eutectode alpha, then cementate. And this pro-eutectode alpha and the eutectode alpha, there is no microstructure change in this pro-eutectode alpha and eutectode alpha. Both are alpha. We can collectively call as alpha, but the formation is at a different stage. Pro-eutectode alpha is formed at a point E, and eutectode alpha is formed at F. That is only difference. Okay.
Sir, that's the difference. Palite eutectode alpha Fe3C.
Palite in the actually Fe3C plus alpha, eutectode alpha plus Fe3C. Actually structure കാണുമ്പോൾ ഇതാണ് അതിന്റെ ഫോട്ടോഗ്രാഫ്. ഓക്കെ, ഈ സ്ട്രക്ചർ കാണുമ്പോൾ ആക്ച്വലി ഈ പ്രോ യൂട്ടക്റ്റോഡ് ആൽഫ ഇതുപോലെ ഇരിക്കും, വൈറ്റ് കളർ ആയിട്ട്. പക്ഷെ ഈ ആൽഫ പ്ലസ് ഇതില്ലേ Fe3C, യൂട്ടക്റ്റോഡ് ആൽഫ പ്ലസ് Fe3C ഇതുപോലെ ഇരിക്കും. ഇത് ആക്ച്വലി ഒരു പേലൈറ്റ് സ്ട്രക്ചർ ആണ് ഫോട്ടോഗ്രാഫില്. അതുകൊണ്ട് അതിനെ ജസ്റ്റ് സെപ്പറേറ്റ് ആയിട്ട് വിളിച്ചു എന്നുള്ളൂ, പേലൈറ്റ് എന്ന്. ഓക്കെ, ഇത് നമ്മൾ മൈക്രോസ്കോപ്പിൽ നോക്കുമ്പോൾ ഒരു പേലൈറ്റിന്റെ സ്ട്രക്ചർ ആണ്, അതുകൊണ്ടാണ് അതിന് ആ പേര് വന്നതെന്ന് മാത്രമേ ഉള്ളൂ. Actually, this pro-eutectode alpha and eutectode alpha are same in terms of microstructure, but the formation is at different stage. Here, pro-eutectode alpha, this orange color, is formed at point E, and when it is crossed the eutectode line, there is no change in the pro-eutectode alpha. It's remain as same without any change in shape and size. But other alpha is formed, that is eutectode alpha is formed from the eutectode reaction of the remaining gamma particles. മനസ്സിലായില്ലേ?
അല്ല, ഞാൻ ചോദിച്ചതെന്ന് വെച്ചാൽ ഈ പേളൈറ്റ് എന്ന് പറഞ്ഞത് ഈ പ്രോ യൂട്ടക്ടോഡ് അല്ലാതെ ബാക്കി വരുന്ന എല്ലാം പേളൈറ്റ് അല്ലേ?
അതെ, പ്രോ യൂട്ടക്ടോഡ് അല്ലാതെ, അതാ ഈ ഫിഗർ കണ്ടില്ലേ, ഈ ഫിഗറിൽ this white color is pro eutectode ferrite. The remaining, we can see like ഒരു പേളിന്റെ ഷെല്ലിൽ ഇരിക്കുന്ന പോലത്തെ ഒരു സർഫസ് ആയിരിക്കും. അതുകൊണ്ടാണ് പേലൈറ്റ് എന്ന് പേര് വരാൻ കാരണം. ബാക്കിയുള്ള റിമൈനിങ് കോൺസ്റ്റിറ്റ്യൂവൻസ് എല്ലാം ഈ പേലൈറ്റ് പോലെ ഇരിക്കുന്നു. അതിന്റെ കോമ്പിനേഷൻ ഡാർക്ക് ആൻഡ് ലൈറ്റ് കളേഴ്സിന്റെ ഒരു ലെയേഴ്സ് ആയിരിക്കും. അതുകൊണ്ടാണ് ആ നെയിം വരാൻ കാരണം. Okay. The last one is the microstructure of hyper-eutectoid steel. The structure change in hyper-eutectoid steel almost similar. Here in this hyper-eutectoid steel, this is the line passing through the hyper-eutectoid region. At point A, similar to the previous case, the microstructure is alternate phase. Alternate is the microstructure. Gamma grains with a single solid solution is formed at point A. When cross this line, this is the line. When cross this line, at point B, before that, at point S, what happened? Some of the carbon particles from gamma. In gamma, we have maximum composition of carbon 2.14%. And from this gamma, some of the carbon come out from the interstitial position and react with the iron and form Fe3C, cementate compound, intermetallic compound, cementate is formed. And this cementate actually segregate in the grain boundary regions of the gamma phase. Okay, so in the previous case, the alpha segregate in the grain boundary region, the hypoeutectoid case. But here, what happened? The cementate is precipitated. Okay, because here we can see the composition of carbon is higher than 1. It's greater than the previous case. So more carbon is present here. So this carbon come out from the interstitial position of the gamma and segregate in the formation a compound Fe3C and segregate in the grain boundary of the gamma phases. Okay, and Fe3C is formed. Then after that, this Fe3C is there will be a growth for this Fe3C along the grain boundary, and this is the so up to point B. At point B, similar. The only difference between the previous case and this case is here alpha is formed at the grain boundary, but here Fe3 is formed. That is only difference. So at point B, here at point I am drawing. Don't consider this two figure. At point, this is my point C. At point C. Okay. At point C, this is the microstructure. At point C, the remaining particles are gamma. All particles are gamma grains, and this cementate, which is formed at point C, is segregate along the grain boundary. This is the cementate formed along the grain boundary. The previous hypoeutectoid steel, it was alpha, but here it is cementate. That is the only difference. So cementate is formed along the grain boundary. Okay. So that is at point C. And at point B, what happened? All the cementate is occupied in the grain boundary regions. So all the grain boundary regions is filled with the cementate particles. Okay, cementate particles. Fe3C particles is filled in the all grain boundary regions of gamma at point B, just above the eutectoid line. When it is crossed this eutectoid line at point D, so there nothing will happen for this cementate. The green color cementate will not change its shape or size when it is crossed this eutectoid line, similar to the previous case of alpha. Okay, and this is called pro-eutectoid cementate, Fe3C. Pro-eutectoid cementate. And what is the microstructure at point D? At point D, this is the microstructure at point D. At point D, we can see there are some gamma particles all the gamma particle when cross this eutectode line convert into similar to this case. Similar to this case, when gamma particle cross the eutectode line, convert into the layered structures of alpha and the cementate. Right. So all the remaining gamma particles, all the remaining gamma particles in this structure convert into cementate. Sorry, convert into alpha plus cementate. Okay. So I am drawing the same figure. So this is the figure, and there nothing will happen for this pro-eutectode cementate when it's changed from B to D. So I am redrawing this pro-eutectode cementate. So this is the pro-eutectode cementate without any change in the microstructure of or the proportion of pro-eutectode cementate. This is the pro-eutectode cementate. Okay, but this gamma particle, when cross this eutectode line, convert into the layered structures of alpha plus cementate. So this will be the here in this region. This region is cementate. So is similar to the previous case, hypoeutectode case. In the hypereutectode case, the only difference is that the pro-eutectode alpha changes to pro-eutectode cementate. That is the only difference. So here it is pro-eutectode cementate, and this one is from the layered structure, that is Fe3C cementate, and this white color is alpha. White color is alpha, and again this can be called this alpha plus Fe3C. This region is like a palette structure. This can be called palette. So all the gamma particles convert into palette, and this at the point B, all the pro-eutectode cementates are formed. So this is a microstructure. We can see palette, eutectode Fe3C, pro-eutectode Fe3C, and alpha. So the only difference is this: here alpha is formed in the form of pro-eutectode state. Okay, so here pro-eutectode alpha is present, but in case of hyper steel, pro-eutectode cementate is present. That is the only difference. Okay. Any doubt? Okay, now let him. The microsystem must have to പഠിക്കണം കേട്ടോ. So this is the photograph of the microstructure of this point I at this region. This is the photograph. Here we can see this along the grain boundary, similar to this green color. Pro-eutectode cement is along the grain boundary. We can see the pro-eutectode cementate, and remaining is the layered structures of cementate and alpha ferrite. That is palette. So this is the palette, alpha ferrite, and cementate layered structure, and along the grain boundary we can see pro-eutectode cementate. Okay, any doubt? Okay, ആണോ എല്ലാവരും? So again ഈ പിക്ചേഴ്സ് എല്ലാം ഞാൻ എടുത്തേക്കുന്ന കാലസ്ട്രി എന്നാണ്. കാലിസ്റ്ററിൽ നിങ്ങൾ റെഫർ ചെയ്യുമ്പോൾ അഗൈൻ ഈ പോർഷൻസ് ഒന്നുകൂടി വായിച്ചു നോക്കാം കേട്ടോ, കാലിസ്റ്ററിന്റെ ടെക്സ്റ്റ് ബുക്ക്. ഓക്കെ, ഇതെല്ലാം പിക്ചേഴ്സ് എടുത്തിരിക്കുന്നതും കാലിസ്റ്ററിൽ നിന്നാണ്. എൻഡയർ അയൺ കാർബൺ ഇക്വിലിബ്രിയം ഡയഗ്രം എടുത്തിരിക്കുന്ന കാലിസ്റ്റർ ടെക്സ്റ്റ് ബുക്കിൽ നിന്നാണ്. അപ്പൊ ടെക്സ്റ്റ് ബുക്ക് വായിച്ചു കഴിഞ്ഞ് കഴിഞ്ഞാൽ കുറച്ചും കൂടി ഐഡിയ കിട്ടും കേട്ടോ. വേറെ ഇതില് ബാക്കി എല്ലാ കാര്യങ്ങളും പറഞ്ഞതാണ്. ഓക്കെ, ഇതുണ്ടോ, പേളൈറ്റ് എന്നൊരു വേർഡ് ഇവിടെ വന്നിട്ടുണ്ട്. അപ്പൊ അതൊക്കെ എന്താന്ന് മനസ്സിലാക്കുക കേട്ടോ. ആ മൈക്രോസ്ട്രക്ചർ പഠിച്ചു കഴിയുമ്പോൾ ഇത് മനസ്സിലായില്ല. പിന്നെ ഈ ലൈൻസ് എല്ലാം ഇനി നെക്സ്റ്റ് ഹീറ്റ് ട്രീറ്റ്മെന്റ് വരുമ്പോൾ ഇമ്പോർട്ടന്റ്. അപ്പൊ ആ സമയത്ത് ഒന്നോടെ ഞാൻ ഈ കാര്യങ്ങൾ പറയും. A2 ലൈൻ, A3 ലൈൻ, ACM ലൈൻ, ഈ ലൈൻസ് എല്ലാം ഇമ്പോർട്ടന്റ്. നമ്മളിനി A1 ലൈൻ, ലോവർ ക്രിട്ടിക്കൽ ടെമ്പറേച്ചർ, ഹയർ ക്രിട്ടിക്കൽ ടെമ്പറേച്ചർ, ഈ ലൈൻസ് എല്ലാം ക്രോസ് ചെയ്തിട്ടാണ് നമ്മൾ ഹീറ്റ് ചെയ്യുന്നത്. ഇനി ഹീറ്റ് ട്രീറ്റ്മെന്റ് പ്രോസസ്സിൽ നെക്സ്റ്റ് ക്ലാസ്സിൽ അതാണ് എടുക്കുന്നത്. അപ്പോൾ അത് ചെയ്യുമ്പോൾ നമുക്ക് ഹീറ്റ് ട്രീറ്റ്മെന്റ് ചെയ്യുമ്പോൾ അതിന്റെ മൈക്രോസ്ട്രക്ചറിൽ അക്കോർഡിംഗ് ടു അവർ റിക്വയർമെന്റ് നമുക്ക് ചേഞ്ച് ചെയ്തെടുക്കാൻ പറ്റും. ഓക്കെ, അപ്പൊ അത് നെക്സ്റ്റ് ക്ലാസ്സിൽ നമ്മൾ എടുക്കും. അപ്പൊ നല്ല ഡീറ്റെയിൽ ആയിട്ട് ഈ പറയുന്ന ഇതുവരെ ഈ പഠിപ്പിച്ചതിൽ എല്ലാ പോയിന്റ്സും വിട്ടു പോവാതെ അയൺ കാർബൺ ഇക്വിലിബ്രിയം ഡയഗ്രം മസ്റ്റ് ആയിട്ട് പഠിച്ചിരിക്കണം കേട്ടോ എല്ലാവരും. ഓക്കെ, സോ നെക്സ്റ്റ് ക്ലാസ്സിൽ TTT ഡയഗ്രം സ്റ്റാർട്ട് ചെയ്യും. കൂളിംഗ് കർവ്, ഹീറ്റ് ട്രീറ്റ്മെന്റ് പ്രോസസ് സ്റ്റാർട്ട് ചെയ്യും. വേറെ ഡൗട്ട്? ഇതെല്ലാം
ബൈനറി ആയിട്ടുള്ളത് ഉണ്ടാവും. ബൈനറി
ഈ മൊഡ്യൂൾ ഫുൾ ഉണ്ടാവും.
അതല്ല, ബൈനറിയില് ഇപ്പൊ ഈ അയൺ കാർബൺ പഠിച്ചതിന്റെ കൂട്ട് അതേമാതിരി ഗ്രാഫ് വരയ്ക്കാൻ ചോദിക്കും.
ബൈനറിയിൽ നിങ്ങൾ പഠിച്ചിരിക്കുന്ന കോപ്പർ നിക്കൽ, ലെഡ്, സോറി യൂണറിയില് പഠിച്ചിരിക്കുന്ന വാട്ടർ, ബൈനറിയില് ഐസോമോർഫോസി പഠിച്ചിരിക്കുന്ന കോപ്പർ നിക്കല്, ദെൻ പിന്നെ ലെഡ്, ടിന്ന്, കോപ്പർ, സിൽവർ. അറ്റ്ലീസ്റ്റ് അതിന്റെ ഫിഗർ ഡ്രോ ചെയ്യാൻ, എല്ലാ ടെമ്പറേച്ചറും കോമ്പോസിഷനും എഴുതിയില്ലെങ്കിൽ പോലും അറ്റ്ലീസ്റ്റ് അതിന്റെ ഫിഗർ ഡ്രോ ചെയ്യാൻ പഠിച്ചിരിക്കണം മസ്റ്റ് ആയിട്ട് എല്ലാവരും.
അതാണ് ഞാൻ ഇപ്പൊ ചോദിച്ചിരുന്നത്. അതാണ് ജനറൽ ആയിട്ട് അങ്ങ് പഠിച്ചാൽ മതിയോ?
ജനറൽ ആയിട്ട്